You ready? Okay. All right, going to 4.2, example 3. Here we have this problem here. If I want to use substitution, I can go ahead. This is actually already set up for substitution, right? Because the second equation has y by itself. So I'll go ahead and take that and plug it into the first. So that's going to look like this. 3x, I'm substituting in for y, negative 3x plus 3 equals negative 5. Now I want to solve for x because what I've done is I've created an equation in one variable, right? So I notice right away, oh, I have some like terms. And by the way, that's 1y, so the coefficient was 1. So if I distribute the 1, it really doesn't, it's not going to change anything to multiply by 1. So I see that I have 3x minus 3x. What's 3x minus 3x? Oh, 0 x's. I have no x's. So don't force there to be an x when there isn't one. So now we're left with 3 equals negative 5. What? Is 3 equal to negative 5? No, that's a false situation. Well, what's going on here if I end up getting a false statement and I have no variable x? I have no more variables. What does this mean? Jace? The lines are parallel. What kind of things do parallel lines have? Parallel lines. What do we know about parallel lines? Oh, they have the same slope and they never cross. So I want to go ahead, if I really want to check, how can I check to make sure that these lines are in fact parallel? What can I do to check that? I know what the slope of the second one is. That's negative 3. Could I take 3x plus y equals negative 5? And what's the slope there? How would I know what the slope is? Jace? Yes. Exactly. Y equals mx plus b tells me what the slope and what the y-intercept, 0b. I write it as 0b. I prefer your intercepts to be written. So if I subtract, if I go y equals negative 3x minus 5, oh, now I've written that equation in slope y-intercept. I can actually see that the slopes are the same and the y-intercepts are different. What would happen if the slopes were the same and the y-intercepts were also the same? What would happen then? They would be on top of each other. It would be the same exact line. But here, if I graph two lines that have the same slope, I end up getting two parallel lines. They never cross. So what's the solution then? No solution. No solution, which you can actually write as an empty set. You see that? These little braces here are what we call set notation, and that basically, the fact that it's empty means that there is no solution. The solution set, there's none. There's nothing inside. It's an empty set. Okay, let's look at example 4, because these are really easy problems, but they're also sometimes the most challenging, because a lot of times what happens is if you have 3x minus 3x, a lot of times people will force there to still be an x. Even though there are 0 x's, they'll just say, oh, x equals, and then they'll keep solving. They'll actually decide there's actually one x when there really is none. Okay, so let's look at the next one. The next one we're going to solve using substitution as well. So we have, there's already set up for us. So we're going to go ahead and plug that in to the second equation for y. So we get 9x minus 3. That's the coefficient, so it has to stay out front. 3x minus 4 equals 12. Now, I've done the substitution. I've substituted the first equation into the second, and I'm going to want to solve for x because I have an equation in one variable. That's the whole point of substitution. So you get an equation in one variable so you can solve for that variable. So now we're going to distribute here. You have to remember the distributive property. We get 9x minus 9x plus 12 equals 12. How would that simplify now? 12 equals 12, right? 12 equals 12. 12 equals 12. Is that a true or a false statement? True. And that's because these are my like terms, and when I have 9x and I subtract 9x, I have 0 x's. So that there again, the variable has poof, disappeared. We're left this time with a true statement. So what do you think it means about these two equations then? These are the same. These are the same. Now, I would want to check, I would want to make sure that I didn't make any mistakes and that they are the same line. So I can already tell that the first one is in slope y-intercept form. What I can do is I can take the second equation, 9x minus 3y equals 12, and I can solve for y. Negative 3y equals negative 9x plus 12. I'm going to divide everything by negative 3 in order to get y by itself. Y equals 3x minus 4. And that is the exact same equation as the first one. So that means that I have how many solutions? An infinite number of solutions. The way I'm going to write this is, there's my solution set, my set notation, x comma y such that y equals 3x minus 4. What this is saying is that you have an infinite number of solutions, and this line right here reads such that, so you have an infinite number of solutions such that they are on the line y equals 3x minus 4. Okay? Because here's the thing, you cannot say, like back in Math 60, when you solved an equation that had infinite number of solutions, you used to say all real numbers. Do you remember that? All real numbers? Here, we can't really say all real numbers because it's not every single point, not every single ordered pair that exists is a solution. You know what I'm saying? If I were to graph this, here's my y-intercept, negative 4, and my slope, rise 3, run 1. Okay, so every single ordered pair on the line is a solution because we know that the lines are the same and they lie on top of each other, which is the reason why there's an infinite number of solutions. But only the ordered pair on the line are solutions. You can't say all real numbers because, for instance, the point 0, 0 is not on the line, so it's not a solution. So this is saying you have what we call this right here is we call this set builder notation. Okay, set builder notation, meaning that if you are going to build the set, you cannot list every single ordered pair on the line. Why can't you list every single ordered pair that exists on this line? Because it's infinite, right? Yes, it's infinite. It's every single ordered pair on the line is too many to list. So when I use set builder notation, I'm basically saying my set that I have, my solution set, is infinite, but it's actually not every single ordered pair. Do you understand the difference? Why it's not every single ordered pair that exists on the whole entire coordinate plane? It's just the pairs that are on the line. Does that make sense? Okay, any other questions about that? Woohoo! 8-minute video. There we go. Oh wait, is it done?